So when we talk about prime numbers, right, numbers that are only divisible by themselves and 1, and these have to be positive whole numbers bigger than 1. So for example, 2, 3, 5, 7, 11, 13. These are numbers that are only divisible by themselves and 1. Whereas the number 4 is divisible by 2, the number 6 is divisible by 3, the number 8 is divisible by 2, the number 9 is divisible by 3. So these are the primes, numbers only divisible by themselves and 1, so they don't have any interesting factors that divide them. And there's an infinite number of primes. And as of now, there's no algorithm that we can use to efficiently generate primes. Now we can test a number to see if it's prime. If you want to know, is the number 57 prime, just start dividing it by possible factors. And you know, when you try to divide by 2, 57 divided by 2 is, 28.5. Well, that's not a whole number. 57 divided by 3, well, that's going to be a nice whole number. That's going to be 19. So anyway, 57 is divisible by 3, so 57 is not prime. If you do 59 and you try to divide by 2, 3, you only have to divide by prime numbers, but if you go all the way up, you'll find that none of these numbers divide 59, so 59 is prime. So we can test for prime numbers, but we don't really have a way to generate prime numbers. There's some algorithms like the sieve of Eratosthenes that we can use to sort of, identify primes in a grid. But we don't have an algorithm that you can just, put in an n and get out the nth prime. But in fact, actually we do. It's just not a practical algorithm. But I have a small program called primes. I can say primes 1, I can say primes 2, I can say primes 3, 4, 5, and it's giving me the nth prime. This program only works for the first 5 primes, but in theory this algorithm works to give us all primes for any number n bigger than or equal to 1. And it's a really simple way of doing this. What we can do is basically make a real number, which looks like this. The first digit is going to be the first prime. The next 2 digits will be the second prime. The next 3 digits will be the third prime. The next 4 digits will be the fourth prime. The next 5 digits will be the fifth prime, and so on. And this is just one real number. It's a number, somewhere between 0 and 1. And if we have this number exactly, we can pull out the nth prime pretty easily. So if I break this up, right, if I want the fifth prime, I just need to move over to this fifth block. And how far over do I move? Well, 1 plus 2 plus 3 plus 4 plus 5. Right, so that's 5 times 6 over 2. I have to move over 15 spots, which will bring me right here. And then I take an integer value, which tosses out this part. So now I have this big integer value here. And then I divide by, or I take the modulo with 2 to the 5th. So if I take this number modulo 10,000, it will give me this piece right here. And so, it's not practical because we can't store an infinitely precise real number. Because real numbers, they're stored with just a certain number of bits. But if we could store this exact value, we could, generate the nth prime pretty easily. So here's what the code looks like for this. And it's a one-line function, basically. There's our magic real number x. And we basically, if we want the nth prime, we do n times n plus 1 divided by 2. That's the sum of the first n digits. We raise 10 to that power, we multiply x by that. That moves the decimal point over to come right after the nth prime. And then we do modulo 10 to the n. So if we want, this fifth prime, it's stored as a 5-digit string. And so if we reduce modulo 10 to the fifth, it gives us just this number. And in this case, this always works because there's a thing called Bertrand's postulate, which says there's always a prime between n and 2n. And so as we go to the next prime after 13, we know the next prime is not going to be more than twice this. In particular, it's going to be less than 10 times this current value. So if we add another digit, we've got plenty of space. And in fact, as we go, we're going to have an increasing number of zeros that are just wasted. But that's, that's okay. So yeah, we can write this number out forever, storing all of the prime numbers in it, and then use this code to pull out the nth prime. So that's not practical because we can't store a real number with infinite precision. But it's an interesting notion that inside a single real number we can actually store an infinite number of integers in a way that, theoretically we can pull them out with minimal work, certainly with a finite amount of work. So let's build on that idea and see what else we can store inside a real number.